chapter alkyne and chapter alkene, they are quite related to each other because both of them show the similar type of properties. Okay? So in the case of the alkene and let me take this off. Turn. This is too much. This technology is. There we go. Now I can do this. All right. So in the case of an alkene, remember that there is a double bond. In the case of the alkyne, there is a triple bond, right? So the triple bond means there is a 1 sigma bond, right? And there is a 2 pi bonds. Remember that, right? So the double bond, if undergoes this hydrohalogenation reaction with one molecule of hydrogen and hydrogen halides, the alkyne undergoes this hydrohalogenation with the 2 times of that because there is a 2 pi bonds, okay? And pi bonds, remember that they act as a nucleophile, right? And so there is a 2 times the nucleophilicity of that of the alkene, right? Because alkene has only 1 pi bond, now it's a 2 pi bond. So the bond angle has this type of molecule, alkyne with the triple bonds are linear molecules, straight molecules, so the bond angle is 180. Remember, the bond angle in the case of the alkene is 120. And because it undergoes this sp2 hybridization, here it undergoes this, here the carbon undergoes this sp hybridization, right? sp. So what percentage of the hybrid orbital has a s character? Can anybody tell me? What percentage of sp hybrid orbitals has s character? Percentage s character. Exactly, 50%, right? There you go. And what percentage in the case of sp3? What percentage of sp3 hybrid orbitals has 25%? This, I have to take this phone call, okay? Please. Because this is one student that is calling. One of my students is asking for the medical school recommendation, and it is, she doesn't know what she's doing. So she has been trying to contact me since a week. So I'm sorry for that, okay? Because I have to help everybody, so, right? So she's asking, so. And if you guys need a recommendation in one way or other, let me know, okay? Down the road. I'm sorry, one more time. There's a 1 sigma bond, 2 pi bond, and the bond distance, the bond length is 1.21, right? Because as the single bond becomes double bond becomes triple bond, it shrinks, right? It shortens. Okay. So what does it say at the bottom? The most of the reactions discussed in the alkene also applies to the alkyne, which I already stated. Although the alkyne usually reacts slower, right? The reaction in the alkyne is slower, but once it started reacting, it reacts twice the amount of the than in the alkene reaction. Okay. Alkene. So let's talk about the bromination reaction. I would like to reiterate here and repeat the alkene reaction as well. Okay. So remember that what happened in the case of the alkene reaction. In the case of the alkene reaction, we have a double bond, right? And then hydrogen like this. And then you have a bromine here, right? So how many bromine react? Only 1 mole of bromine react with the 1 mole of this molecule. So the reaction would yield what? You end up getting this type of product, right? 1 bromine molecule add across the double bond, right? So similar to this one, right? In this case, remember that there's a 2 pi bond, right? So 1 pi bond react with the bromine, and then 1 bromine goes here, and 1 carbon, another bromine goes to the another bromine. Remember the reaction is trans. It has to be trans. So do you remember that or not? I have showed the reaction like this, right? So the bromine either comes from the top phase or from the bottom phase, right? Like this. I have shown this mechanism also. And then once you have this type, then you have a the bromonium ion is formed, right? Bromonium ion is formed, and the bromine will come from the back side, and this will suck it up, and as a result of which, I'm going a little bit faster here, because this thing we already talked about in our last class. This is called the trans-bromination, right? Trans addition. So likewise, in this case also, the bromination happens in an opposite direction, right? So at the first, one equivalent of the bromine will add it across the triple bond, and it forms the trans-bromide. Again, since there is a 1 sigma bond and 1 pi bond, now there is a 1 sigma bond, another pi bond, again undergoes a further reaction with the bromine molecule and add across the double bond. So as a result of which, you end up getting 1,1,2,2 tetrabromoethane. So it's a 1, 2, right? So 1, 1, right? 2, 2 tetrabromoethane molecules. Okay. Next reaction is a hydrogenation reaction. Let's rewind whatever we studied in the double bond. Whenever you have a double bond, there is a hydrogen here, let's suppose. And whenever you have a hydrogen and platinum or palladium or nickel, right? So whenever you have these type of a catalyst present, then what's going to happen? The carbon across the double bond, what's going to happen? The hydrogen will be added across the double bond. Is that correct? Do you guys remember that or not? Right? This process is called the hydrogenation process, right? So likewise, if you do the catalytic hydrogenation, right? If you do the catalytic hydrogenation, that means if you use hydrogen in platinum, okay? Hydrogen in platinum, then what's going to happen? This triple bond will go to the double bond, and again, double bond will go into the single bond. That's what's going to happen. Okay? That means hydrogen will be added 2 times, right? Hydrogen will be added 1 time, and then it does you double bond. Double bond will further goes into the single bond. Okay? 2 times. Now, unlike the hydrogen in platinum or hydrogen in the palladium, right? Or hydrogen in the nickel, now if you use hydrogen with the palladium, and that palladium is now called the Lindlar's catalyst. That means Lindlar's catalyst has a palladium and has barium sulfate along with that. Okay? That means the palladium is now adulterated, right? Palladium is now adulterated with the barium sulfate so that the catalytic, activity of the palladium is now get poisoned by the barium, presence of the barium sulfate. So the efficiency will be seized, right? So efficiency will be depreciated, not the seized, depreciated. As it depreciated, if you try to do the hydrogen with the palladium and then presence of the barium sulfate, which we call the Lindlar's catalyst, now we call it hydrogen in Lindlar's catalyst, triple bond will now undergo this addition reaction to give a double bond. How about the further reaction? Further reaction will stop here. Okay? So remember, this is the question in exam and quizzes. Okay? So triple bond undergoes this hydrogenation reaction with the hydrogen in Lindlar's catalyst, and it will give you double bond. And the reaction stops there. Okay? Reaction does not undergo further addition. This type of reaction you can see in the case of the double bond, what will happen? Hydrogen come from the same side, right? Both the hydrogen come from the same side. So this type of addition is called syn addition. If you go backward in the bromination, the first bromination is a trans-bromination, opposite, right? Goes opposite way. But in this case, whenever the hydrogen is present, right, the hydrogen undergoes this addition reaction in a syn fashion. That's why this is called syn addition. I already said it, right, Nisha? What happened? What the barium sulfate will do? Tell me. It reduces the catalytic efficiency of the palladium. Okay? So further reaction cannot happen. Okay? So now, in order for this convert the triple bond to double bond, you can do the Linder's catalyst, right? Whereas if you want to convert triple bond to single bond, you can use regular hydrogen in platinum. Or if you have a double bond, you can still convert that double bond into single bond simply by using hydrogen and platinum. Do you understand this? Right? So remember that bromination is a transbromination, right? Hydrogenation is a syn addition. Don't forget that. So now, how the reaction works in the case of the hydrogen and halogen reaction. Now we are talking here about the hydrohalogenation reaction. In the case of the hydrohalogenation reaction, in the case of the double bond, remember that what happened, if it is the unsymmetrical double bond, suppose there is a R, and a hydrogen, and if you have a HBr, what's going to happen? Tell me. Where the hydrogen will go? Will the hydrogen go to carbon number 1 or carbon number 2? Tell me. Mesa, look at the structure of the compound, okay? Please look at the structure of the compound. This is unsymmetrical double bond. Carbon 1 has a 2R, that means R means what? Alkyl or aryl group, right? And then carbon number 2 has a 1R. So it's an unsymmetrical double bond, right? Where the hydrogen will go. That's right, exactly. The hydrogen will go to the carbon having higher number of hydrogen, right? So what is the name of, what is this rule is called? Yeah. And remember that this rule, you see the spelling is a different, like a book is a difference. Excuse me, sorry about that. So in the, sorry, thank you. In some book it's like a Markovnikov, in some book it is a Markovnikov, in some book is a Markovnikov, and some book is a Markovnikov. So for me it's like a cough. I'll just say cough rule. Okay. In this cough rule, right, the hydrogen will go to the carbon having a higher number of hydrogen. That means it goes to the carbon number this one, right? So you'll end up getting positive charge R, hydrogen, and R, right? This is what's going to happen. And in the next case, what's going to happen? The bromine will come back and attack with a more substituted cation, right? And as a result of which, you'll end up getting, I'm going to write it down right here with a small letter. So R, and bromine, and hydrogen, and R, right? This is what's going to happen in the case of a double bond. Now here we are talking here about the triple bond, and it again follows the same cough rule, right? Markovnikov. So the pi bond will attack the hydrogen, forms the carbon cation, and then the bromine will attack here. So it will give you this type of a bromine. Okay? This reaction actually does not take place this way. Okay? In your book, I think this is a mistake that your book is saying, but I'm following your book, whatever. Okay? So once it forms this compound, again, remember that there's a 1 sigma bond, 1 pi bond. Pi bond further adds the hydrogen bromide to give you this type of compound. In both these stages, it follows the Markovnikov rules. Okay? So, question in exam. So, also, not only the question in exam, maybe in your question and answer, practice question answer also, it might gonna say that what's gonna happen if the alkyne is reacting with one equivalent of, right, HBr. That means the one equivalent means you're going to get only this product. It does not further undergo this chemical reaction. That means we have only one equivalent, right? Because remember that in one compound, there is a 2 pi bonds and 1 sigma bond. Sigma bond does not undergo chemical reaction, whereas pi bond and pi bond undergo this chemical reaction. So one compound has a 2 equivalent of what? 2 equivalent of pi bond. So it can consume 2 equivalent of HBr, but if you provide only 1 equivalent of HBr, then technically you will get this compound as the major product. Did you understand this? Okay. Let's move forward then. Hydration reaction. Let's go back to the double bond again. Hydration reaction, right? And the double bond, something like this, right? Remember, this is the unsymmetrical double bond again, carbon number 1, carbon number 2. In the case of the hydration reaction, we use acid water. This is acid water. Double bond will attack the proton, follows the Markovnikov. Remember that? Follows the Markovnikov. And then what's going to happen? We end up getting RH plus H, and these 3 hydrogen will go here. In the next step, either water or OH minus, right? I'll just write it down OH minus. The OH minus comes here, and you'll end up getting OH being added into the more substituted carbon. And you end up getting this type of bond, right? With the same token, here also, it's the same thing. You have an unsymmetrical triple bond, you have a sigma and pi bond, right? So the pi bond will go and abstract the proton here, right? And as a result of which, you'll end up getting some kind of a adduct here, which in your book is not shown here. So I'm not going to deal with that. It's a complexes form. The mercury is the one that is to come here and then react with the another carbon here. Okay, and then in order to get rid of mercury, then you need to put some kind of a reductant. So that is not demonstrated in your book. Okay, so what I'm going to show you is like a very simple way of reaction. The hydrogen, it follows the Markovnikov rule. Hydrogen will add to the carbon having higher number of hydrogen, and hydroxy group will again, as in the case of the double bond, the hydroxy group will go to the other carbon. And as a result of which, you will end up getting this type of alcohol. So hydrogen is added here, and hydroxy group is added here, right? So now, this type of molecule is called the enol. Enol means in, and OH means what? Alcohol, right? So that's what is called the enol. Okay? And generally, it is also known as vinyl chloride. Okay? Vinyl chloride, because whenever you have a double bond and any kind of a group is present here, directly attached to the double bond, this type of a group is called a vinyl group. Okay, vinyl group is present here. So here, this OH group is a vinyl, right? So it's directly attached to the double bond. If it's a double bond and another carbon, this is called the allyl. Remember that, allyl. This position is the allyl. If directly attached, right? If directly attached to this one, it's called a vinyl. Okay? Alright. So now, this compound is called the enol, and these enols are not stable. These enol undergo the phenomenon is called the ketoenol tautomerism. Okay, it is called the tautomerism. It undergoes this tautomerism. Okay, what does it mean? Okay, so I'll just show you here a quick way of rearrangement. So what's going to happen? This R carbon oxygen hydrogen. In different book it is different, but I will show you the very, very easy one. Okay? Very, very easy. So this compound, what's going to happen? This double bond will grab the proton, right? Grab this proton, and this double bond goes here. So this single bond Now that's a double bond, right? And this carbon has 1, 2, 3 hydrogens. So you have a 3 hydrogen here, a carbon oxygen double bond. Right? Does it make sense? Any question? Okay. No question, right? So this phenomenon, this type of movement of the proton from unstable enol to the ketone is called keto-enol tautomerism. And keto-enol tautomerism is not shown by this type of arrow, okay? We have to show it from equilibrium, just like this arrow and this arrow. So basically, we're trying to show that enol is not that stable, right? So it is forming more ketones, okay? So this is the one, that equilibrium sign you have to show, shifting more towards the ketone. Although we know that it's a ketone is the major product here, there is a chance that just a small amount of enol is also there. Okay, this phenomenon is called the tautomerism, or you can also say that keto-enol tautomerism. And these molecules are now called the tautomers. Tautomers. These are known as the tautomers, like enantiomers, so diastereomers, right? Now these molecules are called the tautomers. Any question? All good, right? Okay, now let's go to another one. So we talked here about the unsymmetrical triple bond, or the terminal triple bond. Let's see one example I would like to give you. What is the difference between R, C, triple bond, and R? Right? So what is the difference here between this? Is that this type of triple bond is called an internal triple bond because it's in the middle of the compound. Like let's say CH3 carbon, triple bond carbon, and CH3, right? This is the internal triple bond. Now, this compound is a terminal triple bond. Terminal triple bond has a triple bond with the extra hydrogen there, right? So, which makes this hydrogen more acidic, right? And then susceptible to undergo chemical reaction under the right condition, right? We know that. Remember that? What is the thing? We know that sp3 carbon hydrogen versus sp2 carbon double bond hydrogen versus sp carbon triple bond, right? You have to have a triple bond carbon hydrogen. Remember that the pKa. We talk about the pKa, right? pKa of this one is around 50. pKa of this around is 44. pKa of the triple bond containing carbon hydrogen is around 25, right? Do you need to remember this number? If you can, that's fine. But in general, what I'm trying to show here is that on going from sp3 to sp, the acidity increases, right? That means this proton becomes more acidic. So now if you supply some strong base, right, sodamide or sodium amide, right? This sodium amide has an amide group which is strong base, right? Very strong base. This will abstract this proton, and as a result of which the hydrogen will shift this way. Or you can write it down this way also. Look, for your convenience, okay? Not actually this happens, but just to understand. R, carbon, triple bond, and hydrogen. That means you can write down H plus here and minus here, right? So basically what happened? This amide abstract the H plus, right? This H plus is gone. So what happened now remain? R, C, triple bond, C, negative charge, right? So R, C, triple bond, C, negative charge is there. So this amide, right? This is called amide, right? It's interesting. This is amide. React with a proton will form the ammonia, whereas now the remaining sodium positive will mix a salt with the triple bond, and this salt is called now acetylide, In some book, it is also called acetonide. Okay, this is called the sodium acetylide or sodium acetonide. This acetylide is highly reactive. Okay, it is highly reactive. It doesn't show any kind of a reactivity anyway. So it is highly reactive. It can undergo any kind of addition reaction and substitution reaction. We're going to talk its reactivity down in the another chapter. Okay? So these are the few reactions of the alkyne, chemical properties of the alkyne. Okay? So now we talk about a little bit about the thermodynamics and equilibrium. If you have any questions, let me know at this time. We finished alkene and alkyne chapter. Okay? This is the thermodynamics chapter, actually. That is embedded in this chapter, which is not supposed to be. Okay? So we're going to start now thermodynamics and equilibrium. Do you have any questions now? Please let me know if you have any questions. Okay, good. So now in this thermodynamics and equilibrium, we're going to talk here about how. Okay, thank you. So thermodynamics, how we're going to do that is, okay. So now thermodynamics and equilibrium talks about whether a particular reaction will occur or not. Okay. Suppose A and B is reacting to give C and D. Now, you may say that, oh, whenever you put the A and B, C and D will form. Well, does it form or not? How can you find out? Right? Suppose if I have like a silver nitrate and then sodium chloride, right? Okay, it does react, yes, whenever you put the water in the solution, right? But whenever it's in a solid, does it react? It doesn't react, actually. Right? But as soon as you put the water, then it ionizes and it reacts, right? So, likewise, now, if I put certain other compounds, right, like let's say the calcium chloride and sodium chloride, does this two compound react or not? Right? Maybe not. It doesn't react, actually, right? Because it just solubilizes in the water. It doesn't react, right? So, how are we going to find out? What are the criteria that is needed for the reaction to occur? That's what we're going to understand in the case of thermodynamics. And equilibrium means which direction the reaction will go. Is it goes more towards the product side or more towards the reaction? Remember that not all the reaction is 100%. We may think that, oh, this reaction is 100%. In theory, it is possible, right? Practically, there is no such reaction which completely converts from reactant to product. Okay? And that's what we need to find out from the equilibrium also. But if any compound gives you like a more than 90%, we call it as a quantitative reaction. We're not going to say that 99%. We're not going to say that like a 99.9% or 100%. That's never going to happen. Okay? We'll say that quantitative reaction. So how are we going to find out, right? Those things we're going to talk here in this chapter. So generally, whenever the reaction is occurring, then we have an equilibrium that you studied in the chemical kinetics, right? In your Gen Chem. Chemical equilibrium gives you the equilibrium between the product versus reactant. Now think that, right? In order for the reaction, better reaction, should the K equilibrium constant, should this equilibrium constant be higher or lower? If any reaction is excellent, right, should K equilibrium will be higher or lower? Is it tough for you? I'm not seeing any answer, right? That means there is some wrong in whatever you study. Okay, therefore it is. Okay, so now remember that if any reaction is forming, use your logic, okay? You have to use your logic here. It's a very simple fact, right? Remember that. What is this C in the parenthesis means? That is the concentration of the C, concentration of the D concentration of A and B here, right? Now remember that if the reaction is excellent, that means the reaction must go towards which direction? Forward direction more. That means you are forming C and D in high concentration, right? So if the C and D concentration is high, that means the concentration of A and B will be what? Low. Is that right? So now, if you have high concentration of the C and high concentration of a D and low concentration of A and low concentration of B, what would be the value of K equilibrium? Will it be high or will it be low? Use your brain. Use your brain. You know the answer. It will be high. There you go. Right? If now the question is, now let me put the same question in a different way. If the reaction is favorable, K equilibrium constant, will it be high or low? If the reaction is favorable means the reaction can undergo this and gives you more product, right? If the reaction is more favorable means it gives you more product. If the more product is formed, the concentration of the product will be high. The product of the concentration of the reactant will be low, right? So anywhere any reaction is favorable, that means equilibrium constant is always higher. Okay? So now let's give you another scenario. There is a reaction where the A and B reacts and give you C and D, and C and D again reacts to give A and B. And at the long run, A is going towards the BC and CD is going towards A. Both ways, the equilibrium is going in the both ways, same way, same concentration is flowing, right? Under that circumstances, what would be the K equilibrium? The rate of the forward reaction and the rate of the backward reaction. Both are equal. Under that circumstances, what would be the K equilibrium value? It would be one Paris. You're right, 1. Right? Why? Because the concentration of the product, this guy, and concentration of the reactant would be same, right? Because this is the rate in forward and rate of the backward is same way. That means 50% of this will form here and 50% will still remain, right? It goes forward and backward. So at the equilibrium, what's going to happen? It would have a same. If you have an X here, it would be X and X would be what? 1, right? Does it make sense? So any kind of an equilibrium reaction have K value 1. Now, if the reaction is favorable, will the reaction would be 1 or more than 1 or less than 1? More than 1, right? If the reaction is unfavorable, will it be more than 1, less than 1, or what's going to happen? It will be less than 1, right? That's what it is. Now you understand the fundamental, right? So I'm pretty sure that up to this point, you guys do not know about this. What is the value? What is the importance of this K equilibrium, right? So now you guys understand this, right? What is the actually K equilibrium stands for, right? So that's what is going on here. It is written down in this stuff, okay, in this slide. So now we move on to another one. So now here we go. If there is a reaction is going on between this acid and alcohol, and it gives you this product like this, right? So now, what does it say? The equilibrium can be shifted by the Le Chatelier's principle, right? What is Le Chatelier's principle? You guys already studied that, right? What does it happen? The reaction can be drifted towards the forward direction, right, by increasing the concentration of the reaction. That's what is the one thing that it says, right? The reaction can be made favorable by increasing the heat, right, or pressure, or using the catalyst. That's what it says, right? So that means, according to the rule, according to the Le Chatelier's principle, it says that it's a principle. It's not the actual things will happen, right? But it works in some cases, but whenever it's a severe condition, it doesn't work, right? But it's just a principle. So whenever you increase the concentration, you use the catalyst, you use the high heat and then pressure, the reaction will go towards the product, right? So now, if you take out, right? If you take out one of the reactants, if you lower the concentration of the alcohol, this is the ethanol, right? If you lower the concentration of this guy, what's going to happen? One of the component is gone, decrease. The rate of the reaction will now go down, right? And you can also explain the same fact with this equation also, right? Because the concentration of this guy, the B, is now gone. That means you're not forming the concentration of C and D will not be higher then, right? That's what it is. So now, but let's come back to this equation. Now, what's going to happen if you have this reaction and you periodically taking out the water? If you take out periodically the water, what's going to happen? One of the component in the product side is what? Periodically gone. So there is no reaction. So forward reaction, these two are the reactants. For the backward reaction, these two are the reactants, right? So if you take out one of the component of the backward reaction, the reaction will also be again favorable, forward for favorable, right? So that's what the Le Chatelier's principle says, right? So now let's talk about the type of reactions, right? So again, let's go back here one more time. So there are basically two major types of the reaction. One is the favorable reaction, another is the less favorable reaction. Favorable reactions are also called spontaneous reaction, and another one is the non-spontaneous reaction, right? Spontaneous reaction, it happens automatically. Whenever you put it, due to the energetics, it's forward. But the unfavorable reaction does not mean that it does not take place, right? You can force the unfavorable reaction towards the favorable reaction by increasing the concentration, by using the catalyst, by using the heat, and then pressure. Okay? So based off of that, we can categorize the reaction into the two major groups. One is the exothermic reaction, and another is the endothermic reaction. Exothermic reaction, spontaneous chemical reaction, and it releases the heat. Okay? It releases the heat. And the change in heat, you see the change in heat is always less than zero. Less than zero. Okay? The heat of the reactant is always higher than heat of the product. Okay? So that means you're losing the heat, right? So it can be negative charge there. Okay? Delta change in heat. So something like this. So if I have a delta H means heat H of what? H of product, right? Minus H of reactant. I think this is supposed to be, I don't know, E minus D. I don't know why they have put it. It's supposed to be C and D here. I understand it. Okay. So whenever you... No, hold on. Yeah, that's what it is. Yeah, that's okay. So changing... H means what? Heat in the system, right? Heat of the reactant and the heat of the product. So if you subtract that, if this becomes negative, that means this is called spontaneous reaction and it's called the exothermic reaction. So you can see this path is the energy, this is the coordination of the reaction. If you proceed the reaction, you'll end up getting reactant to the product side, right? So A and B reacting to give AB. Which is correct. Yeah, I think it's correct. AB is the product, right? So A and B reacting to give AB as a product. So on going from here, the AB has a high energy than the product, right? So whenever you have that, you will end up getting negative. So change in delta H is negative means it's the exothermic reaction, and those are spontaneous reactions. Okay? So now in contrary to that one, if any kind of a reaction is occurring, which is the non-spontaneous, right? Non-spontaneous reaction. That means A and B will form the product, right? But it doesn't product itself, right? You have to use some kind of external energy. If you supply the energy, then A and B will move towards the product side, right? So under these circumstances, you can see that A and B has a lower energy than the product, right? So in this case, delta H is what? Will be positive. Does it make sense? Yes, no. So remember that whatever you studied in the thermodynamics in Gen Chem, delta G is equals to delta H negative T delta S, right? So delta H means heat of the reaction. Delta G is the free energy, right? T is the absolute temperature, whereas the S is the entropy, right? Change in entropy. Remember that. Okay? And whenever the reaction is more favorable, that means delta G has to be negative also. Okay? Okay. So transition state theory. What the transition state theory means? Suppose whenever there is a A and B is reacting, right? They must collide with each other, right? They just break the bond, they bend the bond, right? And finally they come on to the conclusion that, okay, let's make a bond here, right? And let's have something leave, right? So organic chemistry generally have something if something is coming, something has to leave, or some kind of addition reaction can occur here, right? So suppose if A and B is reacting and it's giving you AB a product, right? AB as a compound, right? So under that circumstance, whenever the A and B reacts, then there is some kind of a first of all tends to make a physical interaction between them, right? That's sort of like a state where A and B is trying to come together and forming a kind of a bond, right? That state is called a transition state. And this transition state always have a high energy and is always represented in a parenthesis by double dagger line like this. Okay? Okay, so now remember that this A and B, which is the transition state, is always have a high energy. That means if you take a look at the energy of the reactant versus the energy of the transition state, now already I said this has a high energy, so that's why the energy is now high, right? So once it forms A and B is like a fighting for making the bond. Once they form the bond, then they relaxes, right? The energy goes down, right? As the energy goes down and they form the product, now what's going to happen? If this is the spontaneous reaction, right? In that spontaneous reaction, the energy of the product will be less than that of the reactant. Okay? And remember the energy that is needed to cross this barrier, this wall, right? This wall is called the activation energy. Activation energy, right? So if there is not enough activation energy, the compound cannot, right? Compound cannot jump to the active transition state and then gives you the product. Okay, so transition state is a kind of an intermediate step. Okay, but it's not an intermediate. It is a transition state. Is a state where it forms a transient species at the top of the activation energy. Okay, so it doesn't stay like that. And can you isolate this? No, it's very hard to isolate. But you can do the computational calculation in order to see how it exists in the transition state, but nobody knows how can we. Sometimes you can get like a trapping and then do some derivatization. You can do that, but particularly transition state you cannot isolate it. And these facts is important whenever you talk about the biochemistry and stuff of the transition state. Okay, that is important. Okay, so whenever it forms the transition state, right, it always favors the path which gives you some kind of a stable intermediate. Okay, what does it mean? So suppose if this reaction is happening, you can see that unsaturated, unsymmetrical double bond, right? Suppose if the reaction is happening like this. In this reaction, in the hydrohalogenation reaction, here we are talking here about the addition of the HBr. So now remember that whenever the hydrogen is added across its double bond, right, this double bond can add the hydrogen in the carbon number 1, 2, 3, carbon number 1, and forms positive charge here, or it can go to this hydrogen, the carbon number 2, and then it forms the carbocation, this carbocation, right, primary carbocation. So this is the primary carbocation, this is the secondary carbon. Now think that what we studied earlier. We studied that secondary carbocation is more stable than primary carbocation. Did we study that, right? So if the secondary carbocation is more stable than primary carbocation, what is the reason? Why secondary carbocation is more stable than primary carbocation? Can you tell me? What causes secondary carbocation is more stable than the primary carbocation? You remember the word. It starts with letter H. Higher quant, candle. It's a hyperconjugation. This is the third time I'm saying, right? Hyperconjugation. So with the hyperconjugation, the secondary carbocation is more stable than the primary carbocation. Okay, now tell me, now use your logic. What do you mean by the stable? What do you mean by the stable? Stable means what? Low energy. Does it make sense? If you're unstable means what? You have a high energy. When somebody wants to punch somebody, what's going to happen? Remember that. What's going to happen in your head? What's going to happen here in your body? A lot of energy comes. You want it to punch, right? That's what it is. High energy means what? You become unstable. Does it make sense? So that means less stable. That means like an unstable means what? High energy. High energy has always unstable. Whichever have a stable. Stable means what? That person who is trying to fight, first of all, think, right? Oh, should I punch it or not, right? That's what you're going to think, right? So the energy is what? First, a little bit what? Lesser. So that's what he's talking here about the energy of the transition state here, right? Energy of the intermediate. So here you can see that in this case, of propene, you have a secondary carbocation and the primary carbocation. Which one is stable? Secondary is stable. Which one is unstable? Primary is unstable. Primary energy is unstable means primary has a high energy, right? Make sense? Right? If primary has a high energy, that means look at the wall, the energy wall, right? This is the energy wall. So in order for this reaction to go via the primary carbocation, it has to cross the tall wall, right? Tall activation energy, right? So it takes a long time and a lot of energy. It is possible, but still it takes a lot of energy. But does it available or not, right? Now the next one is what? Secondary carbocation. In the secondary carbocation, look at the activation energy. The activation energy is less, right? So what's going to happen? So whenever you step into the stairs, would you like to go from 1 to 5th, or you would like to go to 1 to 2 and 3 and 4, right? That's what it is. Because going from 1 to 2 to 3 to 4 is easy, right? So whenever you do that also, it's the same thing. You cannot go from 1 step to the 10th step. Rather, you can go from 1 to 3 steps, right? So it's always favorable because it's just stable, right? If you go to the higher level, you need a lot of energy, and it's unstable. You may fall down. So fall down means what? You may fall down if you jump from, right? If you jump from the bottom here to the 10th, you may fall down here again, right? So it takes a long high energy. So you also always go from the low energy, stable intermediate to give you the product. That's why here also in the case of the addition of the hydrogen and halogen, the reaction proceed via secondary is more stable and more favorable than perceived by other primary publications. Okay, any questions? Okay, so I'm going to stop it here, right? And then now in the